Okay, so a little bit of electrochemistry now. First thing it's asking you to do, as they very often will do, is just to draw a cell to measure the particular voltage that they're interested in. So that's the bare bones of almost any electrochemical cell that you must have. So 2 electrodes, one dipping into each half cell, wire connecting them with a voltmeter on it. And this thing you need to label is a salt bridge, which also connects the 2 cells, 2 half cells rather. Then you've got to decide what actually goes into each half, and in this case on one side, so let's choose to make it on that side, we've got system 2, which has Fe3 plus and Fe2 plus as the oxidized and reduced forms. So those are both aqueous ions, and so they both mixed up together go into the solution. So it's very important that you remember that everything relating to a given half reaction goes into one half cell, and then completely separately everything relating to the other half reaction goes into the other half cell. So Fe3 plus and Fe2 plus aqueous both go into solution in there. You've got to make the electrode out of something, and it can't be iron, it can't be anything that will actually become involved in the reaction, so you make it out of platinum. And that's it, that's all you need on that side. Over here we've got system 4, so that has Ag plus and Ag. So this time the Ag plus goes into solution, and Ag is a metal, so you just make the electrode out of that. So you don't need platinum this time because silver is involved in the reaction, so because it's a metal you can make the electrode out of it. And that's all you need on that side. Now in general, in questions like this, you need to worry about, has it specified that it's going to measure a standard potential, in which case you need to indicate what all the standard conditions are. It's slightly unclear in this question because the values that it's talking about in the table are standard potentials, but then in the question it just says that it's talking about an electrochemical cell based on these redox systems. So it's slightly unclear. In fact, in the mark scheme you didn't have to specify them, but I would have done, because I don't think the question's very clear in the way it's worded. So I would have said that all those ions are going to have to be at 1 mole per dm cubed, and that the temperature is going to be 25 degrees C. You've got no gases involved, so the pressure's not really an issue, but where it is, remember the pressure has to be 1 atmosphere. You certainly wouldn't lose marks for putting those in, and as I say, I think because the question's not very clearly worded, I would have been inclined to worry that they might have wanted that. Okay, then it says, what are the charge carriers that transfer current through the wire? Well, what moves through wires are electrons. So remember, electrons will travel from the negative electrode to the positive electrode through the wire. Through the solution, on the other hand, it's ions that move. The electrons can only travel through the metal bits. Through the solution, including through the salt bridge, it's ions that move. So the overall cell reaction for this, you've got to decide which half reaction is going to go in the oxidation direction, which half reaction is going to go in the reduction direction, because you've got to put a direction on the overall reaction. So, excuse me, what you have to remember is that the half reaction with the more positive E0 will go in the reduction direction. That link between positive and reduction on the one hand, negative and oxidation on the other hand, is the key thing in electrochemistry. So remember, somehow, positive goes with reduction, negative goes with oxidation. So in this case, if you look at the two E0 values, you can see that Fe3 plus, Fe2 plus has a electrode potential of plus 0.77, whereas Ag plus and Ag has a potential of 0.34 volts. So it's more positive for Fe3 plus, Fe2 plus. It's a more positive value, so that will be the positive one, that will be the negative one, and positive goes with reduction, negative goes with oxidation. Okay, so that's the thought process you need to go through, and obviously the sensible thing is to write that down in your working. And then you've just got to apply it to the half equations that you've got. So we're saying that the Fe3 plus Fe2 plus 1 goes in the direction of reduction. Reduction is gaining electrons. In other words, it will be the forward reaction there. So we'll have Fe3 plus gaining an electron being reduced to Fe2 plus. The silver plus 1 is going in the oxidation direction, which is losing electrons, so it'll be the backwards direction there. Silver losing an electron to form Ag plus. So those are your two half equations, and normally what you then have to do is to multiply one or other of them up to make the electrons balance out, but you can see in this case there is only one electron in each case, so they simply add together straightforwardly without any further fuss, and you get Fe3 plus Ag goes to Fe2 plus Ag plus. And always when you've been through a process like that, check that your final equation balances, not just in terms of the atoms, but in terms of the charges. So we've got 3 plus total on the left, 2 plus and 1 makes 3 plus on the right. So that looks good. The cell potential is just the difference between the two electrode potentials. So it's 0.77 for that one minus 0.34 for the other one, which comes in at 0.43 volts. Remember that the cell potential doesn't have a sign, so if you'd done it the other way around, your calculator would have said minus 0.43, but you ignore the minus sign, so you get the same answer, 0.43 volts. Okay, on to part B then. What we've got to do is to identify from that table something, first of all, that will oxidize Fe2 plus to Fe3 plus. So again, you recognise that if Fe2 plus is going to Fe3 plus, it's losing an electron, so that's oxidation, and that must mean that this must be the more negative E0 value. So if we're trying to find something that can make that happen, you need something with a more positive E0 value. So you can choose any system that has a more positive E0 value than Fe3 plus Fe2 plus, which means either Cl2 and Cl minus, or oxygen and H plus, and water. But it's not enough to identify the system, so you've got to choose one or the other. But the question is, what would you add to the Fe2 plus? Would it be the chlorine or the Cl minus? Would it be the oxygen and H plus, or would it be the water? So what you have to think is, well, if this one is going in the oxidation direction, these ones are going to have to go in the reduction direction. So the thing that you add will be the thing that is going to be reduced. In other words, it will be the chlorine would be an answer, because chlorine gains electrons to form 2Cl minus. So one possible answer would be chlorine, or in this case, again, it would be the O2 and H plus, because O2 plus 4H plus 4 electrons goes to 2 waters. So it's the oxygen that's gaining electrons, the oxygen's being reduced. It's important, and they specified this in the mark scheme, if you just said oxygen, you wouldn't get the mark. Because that half equation requires H plus, you need to specify that oxygen and H plus would be needed to oxidize the Fe2 plus. So either of those would do for that one. Then we need a species which reduces Fe3 plus to Fe2 plus, but not Ag plus to Ag. So again, just get it clear, write it down, don't just try and do it in your head, because that way you make sure you get it right. So it says Fe3 plus goes to Fe2 plus, that's reduction. So that must be more positive than the thing that's making the reduction. In other words, we're looking for something that has a less positive potential than that half reaction. On the other hand, we've seen that Ag plus does not go to silver. In other words, for that half reaction, the preferred direction is oxidation. So that one must have a potential that's more negative than the one we're looking for. In other words, we're looking for a system which has a potential in between those two, and the one that fits the bill, and the only one that fits the bill in the table you're given there, is iodine and I minus. Okay, so I2 and I minus fits the bill because its potential comes in that range in between those two. But again, you've got to decide, is it the iodine or is it the I minus that you would add? If it says what species, you can't just quote both sides of the half equation. It's going to be one or the other. So if it's going to reduce Fe3+, it itself is going to have to be oxidized, and the thing that will be oxidized is the I minus. Okay, so I minus goes to a half I2 and loses the electron. So I minus is what you would add, because that's the oxidation direction. So if that oxidation occurs, that reduction occurs. So I minus is the answer. And then finally we're on to fuel cells. They are very keen on fuel cells, so make sure you know this stuff. An important difference, first of all, between a fuel cell and a conventional electrochemical cell. Fundamentally, the difference is that in a conventional electrochemical cell, all the reactants are contained within the cell, so there's a finite supply of the reactants. In a fuel cell, you continuously replenish it with fuel and with oxidant, and as long as you do that, the cell will continue to operate. Okay, so that's the difference. The conventional cell is a closed system, the fuel cell is an open system. You continuously replenish it with fuel and oxidant, and so long as you do that, it will operate indefinitely. An equation for the reaction that takes place in a hydrogen fuel cell. All you have to remember there is that it's just oxidation of hydrogen. So just as if you burnt the hydrogen, the same reaction occurs, but now in a much more controlled way. So the reaction is simply hydrogen plus a half O2 goes to water. Or if you prefer, 2 hydrogens plus O2 goes to 2 waters. And that's all you need. 2 ways that hydrogen might be stored as a fuel. The issue with hydrogen, remember, is that it's a gas and it's just impossible to store hydrogen at atmospheric pressure in any meaningful quantity, because you just need enormous tanks. So the options are, you could pressurize it to reduce the volume. That would get you a mark. Or you could liquefy it by cooling it down, possibly with pressure as well. And again, that would reduce the volume. Or you can adsorb it on a suitable surface. And you can get much higher concentrations of hydrogen by adsorbing on a surface, for example, a nanotube surface. Or you can absorb it into some kind of metal alloy which has gaps in it that hydrogen can fit into. So absorption into a solid or adsorption onto a solid surface, either of those would also do. And finally, why do some people consider that hydrogen fuel actually consumes more energy than using fossil fuels? Well, because it requires energy to produce the hydrogen in the first place. You know, so you can produce it by electrolysis of water or by reforming, various reactions using conventional fuels. But you always have to put energy in to make those things happen. So that's probably the best answer. But you could also make the point that construction of the fuel cells itself is energy intensive. It takes lots of energy, for example, to produce the platinum for the electrodes, to produce the materials for construction of the cell. And that would be another valid answer. And that's it.